good afternoon, everyone. Thank you very much for coming in very quickly. I thought if I rang the bell loud enough, people might think it was intolerable not to come in. So my name's Chris Dent from School of Maths at the University of Edinburgh. So I've worked in energy systems analysis for about the last 12 years in engineering at Edinburgh and then Durham universities, and now I work with a job titled Industrial Mathematics in the School of Maths at Edinburgh. Now, John and Janusz and others gave a very good introduction this morning to why we're all here, so there's no need for me to speak for any length of time. So I'm very pleased to hand over to Cathy McClay from National Grid, who will give the first presentation of the afternoon.
Thank you. I don't know why in every single conference I go to or seminar I get the afternoon slot straight after lunch, but it may be something to do with, I think it's physically impossible to sleep through me talking, but we'll see about that. So what I'm going to do today is, I'm not going to have any equations, I'm not going to have any solutions. My job here is to tell you about the interesting problems we're trying to solve and get some of the creative juices flowing, if you like. I'm head of future markets. I joined National Grid 3 years ago as head of commercial, and in that job I was responsible for setting up everything for the control room, everything from demand forecasting, trading, making sure we had the right services. And now I'm looking a bit further forward, making sure that the gas, electricity, balancing markets, capacity markets can help us deliver to 2050. So what I thought I'd do today is just start with talking about what's changed in the last just 5 years, because 2050 is still quite far away. Hopefully I'll be retired on a beach and all that kind of stuff by then. But if you just look at the plant mix in 2012, we had about 26 gigs of coal, 35 of gas, 9.5 of nuclear, by 8 gigs of wind and 1.8 gigs of solar as the mix on the system. And there'll be prizes for people who can recognise the power stations as well afterwards. It's changed now. In 5 years, the volume of coal, capacity of coal is halved. Gas has stayed broadly similar, but actually there's been a big change in the gas plants and a lot smaller distributed plant as well. We've had one Magnox reactor shut, Wolfa, and one unit. 10 gigawatt growth in offshore wind, mostly, some onshore. And at the end of 2017, it was 12.5 gigawatts of solar in the system. It's now about 13.5, and that's been a massive growth in the last 5 years. And what's really driving that? Well, decarbonisation. We've got 4 times the renewables we had in 2010 on the system. We have 3 times more distributed capacity on the system. That means stuff not connected to the transmission system, but in the distribution network instead. And then we've got a lot of digitizations unlocking so many opportunities. We talk about smart meters there, but being able to aggregate loads, offer services to us. So a huge change in just 5 years. So just imagine what might happen between now and 2050 in terms of change. You know, a lot. So, and just to give you a feel for, we keep talking about this renewable future as though it's in the future. It's happening right now, and just thinking about the things we deal with in the system. 24th of April, this was summer just gone. We had GB running without coal for 76 hours continuously. Then we had in May, solar output was 28.5% of all the generation in one of the half hours. On the 27th of June, it was a nice summer, we had over 9 gigawatts of solar on the peak. And to give you a feel for that, demand was probably about 30-ish gigawatts. That's pretty big proportion. And actually we had the first time that demand was lower in the afternoon than it had been the night before. So we're seeing that sort of duck thing already in the UK. And in July, we had, by 13th of July, there was over 1,000 hours without coal. There's a really good little app that tells you what's running on the system, and you can check how many continuous hours, etc. it's been. So this is what we're dealing with right now. So I'm going to talk about the problems we've got right now because they're going to be magnified going forward. And we publish in the system operator future energy scenarios that you can find online. And we've published 4 scenarios. There's no probability against each of them. But when you look at them, in our FES scenario, by 2030, we've got between 3 and 11 million electric vehicles. Somewhere between 37, I always think 37 is far too nice, and 50 gigawatts of wind on there. And then the other thing is, we're going to have lots and lots of smaller and smaller participants in the system, maybe dealing with thousands of people in the system. So we've got a really uncertain future. And this is one of the reasons I joined Grid 3 years ago. It's just so cool. There's so many interesting problems to solve, and it's right at the center of everything. So just to explain what we do in the system operator, we don't own the wires or there's 3 transmission operators in the UK. There's National Grid, there's Scottish Power, and there's Scottish and Southern. In the system operator, we're part of National Grid, but we're in the process of being ring-fenced. We've got our own logo and everything now. You can see down the bottom. It looks very like the National Grid one, but it's got a little bit of orange at the end. And we're responsible for balancing the system in real time and making sure the electricity keeps flowing, the lights stay on. And we're also responsible for the gas as well, but I'm only talking about electricity today. And just to give you the size of it, the actual costs of balancing the system, all our actions in the balancing mechanism in our markets adds up to about $1 billion a year. A little less than that, but it's about $1 billion a year of costs we're managing. And our business as the SO on the electricity side, we're about a £200 million business managing $1 billion a year in costs. So what do we do? This is as complicated as my slides get, and I am an electrical engineer. So the first thing we have to do is manage frequency in the system. A lot of people have been talking about keeping supply and demand in balance. That's about keeping the frequency at 50 hertz inside ranges. Then we have to manage the voltage in the system, because if we don't manage the voltage in the system, power doesn't flow. It's as simple as that. We've got to manage we talked about constraints earlier. We have to make sure there's no thermal overloads. We don't have a particularly constrained system. The big constraints tend to be Scotland to England, where we've got a lot of wind in Scotland. And then the one this really wasn't a big problem when I joined only 3 years ago. We have to manage the rate of change of frequency. And this is the big change due to the renewables. Most people think about renewables in terms of intermittency. They've also got another property. They're connected to our power system via power electronics, and they don't exhibit any inertia. So if you take a normal big generator, it's a big mass, rotating mass in the system. If the frequency drops, that mass slows down a bit, and the generator releases some energy back into the system, which helps the frequency. When you've got wind farms and solar connected to the system, you don't have as much rotating mass. So if you get a shock in the system, like a generator falling off, the frequency moves much more quickly when you've got lots of renewables on than when you've got lots of thermal plant on the system. Does that make sense? Yeah. So in winter, I don't really care about that rate of change of frequency. I've got all the generators on in peak demand. Winter overnight, I still have to care about it a bit, I guess. But the reason it's a problem is twofold. If the frequency moves too quickly, it can just run away. But the other problem is a lot of these wind farms and solar are connected to the system by rate of change of frequency relays. So if they see the frequency moving very quickly, they think they've been islanded, there's a problem with the system, and they switch themselves off. And we've got a bigger problem. And it could run away with ourselves quite quickly. So we have to manage rate of change of frequency, and that makes it more interesting as a problem for how you schedule and stuff, because you've got the differential of a variable in there now as well. So having enough inertia in the system versus the largest loss that you might have there becomes really important. So they're the things that we look at. So what has happened with all those renewables and stuff? What are the impacts? So I'm going to talk about the impacts, and then I'm going to talk about the sorts of problems we'd like help with solving. So the first one is we've got a lot more of the generations connected to the distribution system now rather than our transmission system. And I'm not precious about where it's connected, but the problem is when it's in the distribution system, I don't necessarily even know it exists. I don't have access to metering a lot of the time. So actually begins to be problems like how do I forecast demand in my system, etc. And visibility of this stuff and actually historical data, so when we're thinking about the capacity market, how reliable it is, this stuff all becomes important. We used to work out how much solar there might be by looking at the register of who registered to receive subsidies. We don't even have that now, so we're having to play around a lot to find things out. Next thing is, it used to be you had a bunch of big generators in the system, so you had a lot of big central generators, and we've moved to managing a system with a number of large generators to lots and lots of smaller sources. So then you get interesting questions about data, control systems, actually sending enough instructions out to manage stuff, etc. So that's the next big change. Uncertainty in the system's increased. A lot of that's brought about by the intermittency of wind. So on a day when we know there's going to be a lot of wind and solar, we will have more frequency response on the system and more reserve on the system. So frequency response is like our cruise control. It's generators just moving up and down to keep the frequency right. And then reserve is the stuff that replaces it when things go off for longer. We've got much more uncertainty in the system. We have to be deciding how much of this to buy. But some days the wind, you think there's going to be 5 gigawatts, then they'll turn out to be 1. We've done a lot of work with the Met Office and solar forecasting. But in the early days, I would get a solar forecast, which would say it's this number plus or minus 2 gigawatts was the solar forecast for the hour. Plus or minus 2 gigawatts is 2 full coal stations, difference between the lowest and the highest. That's quite a lot of uncertainty that you're dealing with. Dynamics of the system's changed. I've talked about this. The inertia has changed on the system. And so the control of it and how we even design our services, are they quick enough to manage things? That has changed a lot. And actually modeling the system. We need more flexibility on the system to manage the intermittency, to manage the rock-off. We need a lot more flexibility, and that sounds easy, just have a lot more flexibility. But the thing is that I actually get a lot of my flexibility services from rotating thermal plants, so things like coal plant, gas plant that's on the system will provide the upward and downward regulation a lot of the time. But if I'm in the summer, I've got 10 gigawatts of wind on. How much is nuclear now? I never remember, Alistair. 8 or 9. I've got my solar. When you stack that up against demand, there's not actually very much space to get any of that thermal plant on to provide the upward and downward regulation. So we've had to do a lot of work. We've got a program called Power Responsive, where we've been really encouraging demand side response, so moving away from the paradigm of generation follows demand to actually we've got a lot of this low carbon generation on the system. Keep it on as long as you can and have demand follow that. And if you look at something like our frequency response service, 3 years ago we would have 20 tenders come in a month, and they'd be mostly from traditional generators and stuff. Now we have about 200, 300 tenders come in a month, and 40% of all the tender volume is from non-traditional providers. That could be aggregators, demand-side response. It could be small generators embedded in the system, etc. A lot of batteries, because a lot of money got poured into batteries and they're now trying to find things to do with them. So in the last 3 years, as a result of this, the price for that service has dropped from £15 a unit to about £3 a unit. And I like to take all the credit for that, but it's all to do with people investing in batteries. So this is the next one, changed understanding of security of supply. And Chris and I were talking about a bit about this over lunch, that we've got the concept of loss of load expectation, etc. But As you have more intermittent generation on the system, what does that distribution of uncertainty actually look like? What does the tail look like? As you move to having more smaller units, how does that affect things? How do you actually, so for instance, storage we can't control at the minute. How do we think about security of supply in a highly dispersed world? And how do we think about things like black start, which if everything went, we'd have to bring all the system back up. We've traditionally relied on coal plant and block loading. We've been diversifying sources, and just this month gone, we've won an innovation product, about 10 million, to look at actually restarting the network using distributed sources in the distribution network and not just the transmission one. So just thinking about changing, security of supply has changed. And as I was saying, sources of flexibility have changed, so my traditional generators aren't there, and we've been getting lots of different ones. And then it becomes, how do you know that they're going to be there? How do you test them? How do you validate them, etc.? How do you design the products so that they work for these new sources? Because a lot of the products we had is just what generators could do. But actually, are we creating unnecessary barriers to entry because we've designed it that way, and actually if we just tweaked it, it would work better for everyone. So that's been a lot of my work for the last 2 years. So what sort of things would I like you guys to think about? So then I say, yeah, all those engineering rules of thumb, you know, us engineers, we just use rules of thumb and stuff. We can't anymore because everything's changed. So we actually have to do a lot more modeling and analysis to get safe and economic management of the system. So where are the things I think, some of the areas I think are interesting? Forecasting demand is a great one. We've actually done a lot of work with universities on this. So Sheffield, Reading, we've done a lot with the Met Office as well. And we've now moved in our solar forecasting into using an artificial intelligence model, which retrains. We get our data from the Met Office more often. And it's really interesting, the model has reduced our mean average error quite considerably, but more importantly, the big tails have gone. There's no longer that plus or minus 2 gigawatts going on, and that really helps bring in the uncertainty. So, but there's a huge amount to do on demand forecasting, and if you think about the future where we have lots of batteries as well, most of those aren't on my transmission system, they're on the distribution system. They're price dependent. I don't have any prices in my demand models at the minute. Or is there a philosophy that I don't have to think about demand forecasting in the future where we have less big generators with slow run-up times, and can I just wing it because everything comes on really quickly? So those are the sorts of questions. I don't think as system operator we should wing it, but you know, can we think about different time scales from before? Modeling system dynamics. So, for instance, my team came to, or just before Christmas, the team came to me and said, Cathy, we've redesigned, we're getting rid of primary, secondary response because that overholds. We've designed new response services, and we're ready to go. We're going to tell the market about it. And I said, okay, so who's signed all this off? What modeling have we done? Oh, well, we've done all the modeling with the swing equation. We're really happy. Okay, so what are the limitations? What happens in real life that's not covered in the swing equation? How are we going to make sure this works in real life? Because you're putting the whole of the system on these 4 new products, which look kind of like the old ones. But how do you actually get away from all this lovely theoretical modeling to understand the limitations of the model and the uncertainty and where we need to look at for sensitivities, etc.? We're actually building it into our simulator now, but it's still a model. So the first day if it ever go live, I'm going to be quite worried about it because you're testing your theory on the national electricity system, which seems quite a brave move in my view. So thinking about modeling system dynamics, but also the imperfections in models is really important for us. Designing new balancing services. This has been my life for a year and a half. If you're interested in balancing services, we've got on our website the future of balancing services, I think it is. We've got a bunch of roadmaps saying what we're looking at doing here, and this has been a real success, I think. In actually, the first time I went into a meeting on this, it was in the Hilton in Warwick, in a room without any windows. It was really depressing. I think there was 25 people in the room, and 7 of those were from National Grid. If you now go to one of our power responsive meetings, there's 250 attendees, and it's limited because that's the size of the room we can get. So the number of people who are interested in our balancing services and how you work with such a broad group of people to design services that work has been interesting. And how the markets work. And one of the things I was talking with someone earlier was we're trying to move our services closer to real time. And we've got a response service and a reserve service. I'd like to co-optimize them because you can provide response or reserve. But there's also an energy market day ahead, but that's coupled to Europe, and I'm not allowed to touch that. So how do I get economic, efficient decisions in markets close to real time? Is an interesting equation. It's a question. We're moving to auctions. We've actually signed up with EPEX Spots, and we had some good talks with David in the early days about auctions and auction design. But what sort of auction should we be designing? You know, we're going quite simple initially, but actually designing auctions for close to time, choices for balancing services, maybe even moving within day and very short term as you go on. I may have retired by then, but it's an aspiration. System dispatch and control. One of the things, someone talked about chaos and stuff in systems. One of the interesting things is we're going to have many more controllers across the system, both on the transmission space and the distribution space. You might have DSOs, you've got aggregators, etc., all sending out signals to things. Might you get a situation like high frequency trading in markets? Will the system stay stable, etc.? We're interested in that kind of problem as well. Can we see these terrible events? Low probability, but under what circumstances might they happen? Market design, you know, how we design we've just been talking about some of the things about capacity markets. How do we design gas, electricity capacity markets and services together so that market participants can make efficient decisions? If you're thinking of closing a plant at the minute, you might have to bid for your capacity market over here, but you won't find out if you've got your balancing services to 6 months later, etc. So how do you make efficient decisions in markets, and is there more that we can do to facilitate sort of efficient entry and exit of markets and using market design? And then decision making under uncertainty. Nothing is certain at all, and we have an example of this from we're building a new dispatch system, and it doesn't understand uncertainty enough because it'll look ahead and go, right, I'm going to have to bring this generator on. I will send the signal now, and then half an hour later, I don't have to bring it on anymore. I will tell it not to anymore. But we've got bid offer spreads in our balancing market, and how do you actually guide the system towards the right answer without taking decisions until you have to? And when you've got thousands of units to dispatch rather than hundreds. So it feels more like driving a car down a road than hitting a normal optimization mixed integer program. I've started trying to talk to my friends who design autonomous cars for Apple and things like that. It's probably more of a problem like that. But how do we make decisions under uncertainty? And that can be anything from taking decisions in the market through to how do we dispatch plants and that kind of thing. So they're very broad areas. If anyone wants to talk to me, we can talk in more detail. But I wanted to leave time for questions and clarification. So I've just got 3 summary points here. There's a lot of change going on, and it's going to keep going on, and it'll probably get quicker, is my first one. We need to improve our modelling and analysis and understand the system better because it's so different from what we had before. And I think there's loads and loads of interesting problems for people to tackle. We've had really good progress in things like our demand forecasting, but there's a huge way to go. And hopefully you guys will find some of them interesting. Thank you very much.
Thank you very much. Janusz seems to have a question.
Well, the title of the whole day is 100% renewables.
Yeah.
And I remember about 20 years ago, maybe 15 years ago, system operators were of the view that if it's up to 20%, it's okay. If it's about 20%, the system will fall apart. There's no way we can operate it. We are operating it higher.
Yeah.
As the limit have moved up for
Yeah,
the system operator
yeah, I think so, and it's what you can. So Ireland has got an even higher penetration of renewables than we have. Now they sort the problem basically by having frequency response in every wind farm going, and go from there. I think that to get 100% renewables, we really have to stimulate demand side, etc. And that's the bit I worry about. I think it's doable, but by when is the question. But the limit's definitely going up the whole time. Engineers, by their nature, tend to be terribly conservative, you know, and they keep telling me, Cathy, stop getting 5 megawatt units for the control room and stuff. It's far too hard. But they always find a way to do it, so we just have to keep challenging ourselves and keep pushing it on. If you look at our FES, for our future energy forecasts for 2016, when we were sitting in 2012, we do four scenarios. One of them had 1 gigawatt of solar and the other 3 had 0. Mm-hmm. And we weren't bad at forecasting solar compared to everyone else. Everyone was having those forecasts. And we now have 14 gigawatts of solar, and we manage it, and we find ways of doing it. And it's about finding, a lot of our job is about finding cheaper and cheaper ways of doing it. So we had to throw money initially at the rock-off problem, the rate of change of frequency problem. Now we're looking at, we've done a big program to change the settings on the wind farms. This year, solar connects with vector shift. We have the same problem. If it's anywhere near, we have a fault. We spent £200,000 on it in the run up to the summer and saved about £10 million for this summer because we got rid of that problem. So it's, for me, you can always do it at a cost, and a lot of my job is trying to bring that cost down for consumers.
Any more comments, questions? Patrick?
Yeah, thank you for the presentation. So I was pushing something on the grid flexibilities to play with the switchers and phase shifter transformer, dynamic and rating. Do you have something on this area? Who is taking care of that in case of the splitting between people that take care of the asset and someone that take care of the system?
There's stuff we've been doing on our networks for ages. Like one of our problems overnight is voltage overnight. We actually have a lot of grid supply points just inject VARs into our system the whole time. And so our voltage is high overnight, our lines are lightly loaded as well, it exacerbates the system. So we routinely do things like switch lines out. We've got a project that we're running with UKPN called Power Potential that you can see online, where we're looking at trying to manage some of the voltage using assets in the distribution network and sorting out things like that. One of the DNOs is providing us with, controversially I should add, is providing us with balancing services by switching their transformers. The only problem is there's an argument, are they using regulated assets in a deregulated way or not, so it's interesting. But there's going to have to be a lot more smart use of the system to make things work. And wherever we're looking at an operability issue, there's really 3 ways of sorting it. 1 is you sort the rules, 2 is you build something, or 3 you use a market. So for voltage, we could sort out the rules by saying actually DNOs, you have to keep your power factor envelope between these limits, sort yourself out. Build something, you build a sync comp or something near the problem, or you create a market to sort out the problem in volts. And a lot of what we're all doing these days is learning by doing, so trialing solutions and see what works. Because if we all sit in a darkened room for 3 years trying to work out the optimal solution, life's gone by and the problems have hit the system. So. Does that make sense?
Yeah.
Yeah. Should I just say, can you just introduce your name and institution so people know who you are? Because I probably know who people are, but not everyone will. Ellen.
Ellen Webb on UCL. Are there any data sets that National Grid doesn't have, either because things aren't measured or because it's not accessible, that would help with these problems if you could measure things better? Or know about things in a better way?
The answer is yes. So for instance, when we've been looking at the capacity market this year, We got a lot of data off Electrolink, who have DNO data, to try and work out what are the breakdown rates of generators in this distribution system. But all we get is megawatt hours. We don't actually get what unit it is, what technology it is, or anything like that. So if you look at what we need to do as an industry, data is going to be like one of the underpins everything. And one of my mantras since I joined was we try and be as transparent as possible. We publish a lot more out there than we used to, but there's a long way to go. But we need more and more data to be able to manage the system well. And one of the big changes for us is we've never really seen ourselves as a big data company. We need to be a big data company now to manage the system.
There's one more at the back. David Gowers from Newcastle University. I'm very interested in that thing that you said about reduced inertia. As we go closer and closer to the ultimate limit of 100%, how can you cope without?
Well, you can do things. So first of all, synthetic inertia can get us a lot of the way. Wind farms can provide synthetic inertia to us by switching their power electronics. They just don't. You can have things like pump storage. They can provide inertia for us as well. Nuclear plants provide inertia. There's going to be stuff on the system with inertia, and I think we also just have to say, wind farms, you have to exhibit inertia to us. Yeah. Okay.
Okay, thank Cathy again.